Hello everyone, this is Professor Kuehn. We have been discussing A Student's Guide to the Great Physics Texts, Chapter 3, which is titled Archimedes' Principle and Falling Bodies. And the main issue we've been talking about is the speed of falling bodies and how it depends upon the specific gravity or the density of the body, as well as the specific gravity or the density of the medium through which it falls. Admittedly, for the last couple of lectures, we, like Galileo, have been distracted a bit on some tangential issues that were actually very interesting issues, but let's get back to the main topic of this chapter. That is, how can we understand why bodies with different specific gravities fall with different speeds in different media? So let me write that question out just so we know where we're going with this. So here's the main question that we are discussing. How can we understand why it is that bodies, objects, with different specific gravities. Remember, specific gravity is the density of an object compared to the density of water. So with different specific gravities, fall with different speeds in different media. And I'm going to try to push all the way through this discussion. Okay? So what do we mean? Let me give you a concrete example to think about that will illustrate the problem we're trying to solve. So let's suppose that we have a cylinder, and the cylinder is filled with water. And we are to drop a pebble in this water. So here's a pebble. Okay, so that is a pebble, a little piece of stone. And as it falls, it's falling with some speed. Okay? And we also drop the same pebble in another column, but this column, instead of being filled with water, is just filled with air. So again, we've got the same thing here. We've got the same pebble, but this column, instead of being filled with water, is filled with air. So I'm going to put some dots here representing the fact that this is air. So I'll write air right here, and I'll write water, I guess the chemical formula H2O, right here. And we all know that when a pebble falls in air, it will fall comparatively fast or quickly, and this one will fall more slowly. Okay? So here is an example of a situation where we have different media, different surrounding substances, but the same object. The same object falling through different media. And we know from experience that the pebble will fall more quickly in air than in water. Okay? Now, let's consider a different situation. Again, we might think of a column right here. I'm just going to go ahead and draw the column over here. And now we consider a different case where we have the same surrounding medium, H2O, H2O, but in this case, we drop two different objects. So in one of them, we drop a ball of copper. So this is copper. And in the other one, we drop, what color should I make it? Let's do this. We drop a sphere of aluminum. Okay? And these things are going to, so you might not know this, but copper has a density or a specific gravity of about 9, and aluminum of 2.7, about 3. Okay, and we're going to find that the copper falls with some speed, and the aluminum falls with some speed, and we're going to find that if these are the same size objects, then this one is going to fall comparatively fast, and this one will go slow, if they are, once again, the same size object. Okay, so here, more generally, we're talking about the same medium, but different object compositions, or different objects. So these are the main issues that Galileo, in this chapter of his dialogues, is trying to consider. And remember, he's really reacting to the work of Aristotle, who was aware of these things. Aristotle was aware of the fact that when you have a heavy object, it falls more quickly than a light object in the same medium. And when you have a very dense medium, it tends to retard the fall of an object more than a very undense medium. So now Galileo is going to approach, we're going to try to understand Galileo's approach to the same problem. Okay? So here is the answer. I'm just going to jump right to the answer that Galileo is going to provide. He's going to say, and this is what he talks about in this chapter, that in a vacuum, and again, this is a controversial topic because some people don't believe there can be a vacuum, but he's going to argue that in a vacuum, all objects, get rid of this, all objects would accelerate And I'll say more about this in a moment, what I mean by accelerate, but they would accelerate at the same rate. And that is, the acceleration is about 10 meters per second per second. Okay, 10 meters per second squared. I should mention right away that this terminology is anachronistic. That is, we're using modern terminology to describe something that Galileo was talking about, not using modern terminology. By modern terminology, I mean things like meters. Galileo did not talk about meters because, like I said a couple of lectures ago, the meter hadn't been invented yet. Okay, this, by the way, is about page 39 in the text. What does this mean when we say that in a vacuum, or what Galileo says, in a vacuum all objects would accelerate at the same rate? He hasn't proved this, by the way, he's merely asserting this. He's saying if you drop an object, its speed starts out at 0, but as it falls, its speed is going to increase. That increase in speed we call an acceleration. And what he says specifically is that in a vacuum, all objects accelerate at the same rate. That is, their speed increases at the same rate, and that rate is 10 meters per second every second. So if during the first second an object starts out at rest at 0 speed, by the end of the first second it'll have a speed of 10 meters per second. Its speed continues to increase, so after the second second, its speed will be 20 meters per second. That is, it gained 10 meters per second for every second of fall. That's what we mean when we say that this acceleration is 10 meters per second squared, or 10 meters per second per second. Okay, so this is what his claim is going to be. Again, he hasn't proven this, he's merely claiming that all objects would accelerate at the same rate if they were dropped in a vacuum. So this is in essence Galileo's theory of falling bodies. This is controversial because he's making a claim about what happens in a vacuum when in fact he had never made a vacuum, or he was never made a perfect vacuum anyhow. So his opponents would criticize him for saying, you're talking about a dream world, Galileo. Okay. But, okay, having said this, now let's go on and say what happens when your things are falling in a medium. In a medium, that is not in a vacuum, but in a medium, the acceleration is reduced. It's reduced. Okay? And this is due to the buoyancy, and I'll talk more about this in a moment, the buoyancy of the body. Or I guess we could say the buoyancy, I could say buoyancy of the body. That's point one, the buoyancy of the body and the drag acting on the body. In what follows, we are going to focus on this effect. It's going to be very important to distinguish, and Galileo does this, to distinguish between the effect of buoyancy and the effect of drag. The more simple one to think about is buoyancy. The more complicated one to think about is drag. So we're going to do this one first. But the main issue is when you're in a medium, objects fall at a different rate than they would in a vacuum. And the different rate is determined by the buoyancy acting on the body and the drag. Okay. Another point I'd like to make right away is that objects, after falling for long enough, reach what is called terminal velocity, or a final velocity, a final speed. Okay, why is this? Well, it's because according to Galileo's theory, in a vacuum, an object would simply keep accelerating. You drop it, it gains 10 meters per second of speed for every second that it falls. If there was no drag, no medium that's retarding the fall, its speed would increase indefinitely. But because there is a medium through which it falls, there is a drag force that is going to check the acceleration or reduce the acceleration. So whereas at first it feels an acceleration of 10 meters per second every second, as it continues to fall, its speed increases, the drag is going to increase, and the acceleration is going to get smaller and smaller until finally the acceleration approaches 0, at which point the velocity no longer changes. That is called the terminal velocity, and I'll say more about that in a little bit, but I think it's good to just alert you to that right now. Okay, now the terminal velocity, and again, this is due to drag increasing with speed as the speed increases. We'll come back to this later, but right now I want to focus on buoyancy. Okay, so in order to understand the effect of buoyancy on falling objects, we need to understand something called Archimedes' principle. Archimedes' principle. This is going to help us understand drag, and that will help us understand how a medium can can reduce the speed of a falling object. So in my next lecture, I want to focus on Archimedes' principle.